So the first one here is a subtraction problem. Remember, to add and subtract, we must have the same name. For radicals, that comes down to two things. One is we must have the same index of our radical. And here we do. They're both fifth roots. So that part is met. The second thing we must have is the same base. Well, this one has a base of 96, and this one has a base of 729. Currently, they are not the same base. However, we can reduce the radicals, and it might change the base. It may give us the same base. So for 96, if we factor that, 96 becomes 2 to the power of 5 times 3. In other words, 5 2s and a 3. So that means we can pull out that fifth root of the 2. So in front it's 7 times the 2 times the fifth root of 3. Or 14 times the fifth root of 3. Over here, 729 factors into 3 to the power of 6. Well, what I'm going to do is I can take out 5 of those 3's with the fifth root. I can think of it as 3 to the 5th times 3 to the 1. 3 to the 5th, when I take out the fifth root, is a 3, giving me now 5 times 3 out front with a 3 left inside the radical. So 5 times 3 are 15 times the fifth root of 3. Now that radical has the same name. The fifth root of 3, the fifth root of 3, they're the same. So I can subtract just like I would if it was 14x minus 15x. 14 minus 15 is a negative 1, fifth root of 3. So I can just write as negative fifth root of 3 would be that result. Number 2 over here. Same type of thing. They don't have the same name. They have different objects inside the radicals, but they're both third roots, which means we've got some room to go with it. Well, this one here, I'm going to split it up. The third root of 7x on top, the third root of 64 on bottom, which is just 4. This one over here, I'm going to split up 56. Oops, that's not going to work out, is it? Yeah, it is. 56 is 2 to the power of 3 times 7 times x. So I can factor out that 2 to the third with the third root to get a 2 out front. That's 2 times the third root of 7x. So this is basically 1/4 times the third root of 7x plus 2 times the third root of 7x. 2 plus 1/4. We typically don't use 2 and 1/4 in front of it. We'd make that 9/4 times the third root of 7x. If you wrote it as 2 and 1/4 times the third root of 7x, I'd be okay with that. My math lab may mark it wrong. Any questions on those first two? Okay, so then, let's look at number 3. Number 3, we are distributing 5 times the, I'm going to go a different color, 5 times the third root of 4 times 7 times the third root of 6. Now remember, we can multiply the whole numbers. When we multiply, we do not need the same name. Now we still need the same index of our roots. Third roots can only multiply other third roots. Just like when we multiplied the x's times the x's and the y's times the y's. We'll do third roots times third roots. Other indices of the roots will multiply by the same index. But we can multiply the counts. 5 times 7 is 35. The third root of 4 times the third root of 6 is the third root of 4 times 6 is 24. We're not done with that, by the way. Then we do times negative 3 third roots of 10. 5 times negative 3 is a negative 15. Third root of 4 times the third root of 10. 4 times 10 is 40. If I look at this, 24, if I factor it, is 2 to the third power times 3. I can take the third root of that 2 to the third power, would just give me a 2. 35 times 2 is 70. Leaving me with 70 times the third root of 3. Over here, 40 factors into 2 to the third times 5. Again, being a third root, I can factor out anything to the power of 3. So 2 to the third root of 2 to the third is just 2. 15 times 2 is 30. So that's a negative 30 times the third root of 5. Now at this point, the roots may both be third roots, but they have different objects. One is the third root of 3. The other is the third root of 5. I cannot, since all that's left is to subtract, I cannot combine those anymore. Any questions on that one? Number 4. 9 minus the square root of x minus 3 squared is 9 minus the square root of x minus 3 times 9 minus the square root of x minus 3. We did these last class, we did these multiplying them out long form, but we can just use FOIL if we want to. So let's do 9 times 9 is 81. 9 times negative square root of x minus 3 is negative 9 times the square root of x minus 3. Negative square root of x minus 3 times 9 is another negative 9 times the square root of x minus 3. Negative square root of x minus 3 times a negative square root of x minus 3. Well, negative times a negative is a positive. A square root of x minus 3 times the square root of x minus 3 is simply x minus 3. So a little bit of simplifying to do here. Got the to a negative 9 and negative 9 make a negative 18 times the square root of x minus 3. We got plus x minus 3 over here. The negative 3 will combine with 81 to make 78 minus 18 times the square root of x minus 3 plus x. That's what we get. My math lab may ask you to put that in descending order. So x minus 18 times the square root of x minus 3 plus 78 would be descending order. Any questions on that one? I'm going to have you multiply this one out quick, and we'll talk about it in just a minute. So if we start out, 3 times 3 is 9. 3 times negative 7, square root's 11. 3 times negative 7 is negative 21. Square roots of 11 times the square root of 11. 7 times 3 square roots of 11 is a positive 21 times the square root of 11. And then 7 square roots of 11 times negative 7 square roots of 11. Well, let's do that off to the side here. We've got 7 times negative 7 is a negative 49. Square root of 11 times the square root of 11 is 11. Negative 49 times 11 is negative 539. So as we combine here, negative 21 times the square root of 11 and positive 21 times the square root of 11 cancel out. That's gone. 9 and negative 539 can combine to be just negative 530. So as ugly as this problem is, it combines to give us just a whole number. And the reason for that, we mentioned this term a little bit last week. Those two terms are what we refer to as conjugates. Conjugates are sum and difference product. You'll notice, same terms, 3 and 7 times the square root of 11, it's just one is plus and one is minus. One's a sum and one's a difference. Conjugates, of course, are a sum and difference product, however, where one of the terms is a square root. Not a radical. Other roots it doesn't work for. Only for square roots does this conjugate work. And when you multiply a number, a radical expression, by its conjugate, it will always give you just a single number, an integer in this case. So if I have, oops, get back here. Two square roots of 7. So trying that again, let's say we have 5 times the square root of 7 minus 4. The conjugate of that is going to have the same terms. 5 times the square root of 7, and it's going to be 4, but instead of minus, it's going to be plus. When we multiply those conjugates, we're always going to get a whole number. Doesn't matter whether the radical's in the first term or the second term. 5 square roots of 7 times 5 square roots of 7. Well, 5 times 5 is 25. Square root of 7 times the square root of 7 is just 7. That's 175. 5 square roots of 7 times 4. Well, 5 times 4 is 20. So that's positive 20 times the square root of 7. Negative 4 times the 5 square root of 7. Negative 4 times 5 is negative 20 times the square root of 7. And negative 4 times positive 4 is negative 16. And we notice positive 20 and negative 20 square root of 7 cancel out. 175 and negative 16 makes 159. So why do we care? Why am I making such a big deal about these conjugates? Well, I hinted at it last week. We don't like having radicals in the denominator. It's not incorrect, it's just poor grammar. We've mentioned that idea of grammar a few times this semester. This is one that's considered extremely poor grammar. And I kind of hinted at the reasoning last week. Before calculators that would calculate all these roots out for you, we had to look up all the roots that weren't perfect roots in our tables. And those tables would tell us, if I had the value of x, 1, 2, 3, 4, 5, typically 1 probably wasn't even in it, 6, 7, 8, so on. It would have the square root of x. Well, the square root of 1 is 1. Square root of 2 is 1.4140, blah, blah, blah. Square root of 3, 1.73, again, blah, blah, blah. Square root of 4 is 2. Then it would have, the next column would be the third root, and it would have all those third roots listed, and so on. And so when you did a calculation, you'd have to go to the table, and you'd have to find that value for that root off the table. Well, if I had 5 divided by the square root of 2, I would have to take 5 and divide by 1. Let's actually do the square root of 2 here, see what it is. Actually, 1.414214. I don't know about you, but I don't really want to dig into dividing that out. 1.414214 going into 5. That's going to be ugly having to divide by that big of a decimal. And that's still just to round it off. So if I do something called rationalize the denominator. And what that is I'm eliminating all those radicals from the denominators of my fraction. So instead of 5 divided by the square root of 2, I'm going to rename that fraction, redo that fraction, so that there isn't a root in the bottom of it anymore. Remember, we can multiply the numerator and the denominator of a fraction by the same number. Since this is a square root of 2, if I multiply by another square root of 2, square root of 2 times the square root of 2 is just 2. It eliminates that radical. I have to multiply the numerator by the same thing. 5 times the square root of 2 is 5 times the square root of 2. Now when you look at these, 5 over the square root of 2 actually looks simpler. There's less numbers involved, less terms there. But this is actually a lot simpler to calculate if you had to use these tables. 5 times the square root of 2 divided by 2 is way simpler than just dividing 5 by the square root of 2. Remember that ugly long division. 5 times the square root of 2 would be 5 times 1.414214, however many digits that goes out, which is way easier to multiply by that ugly number than it is to divide by it. And then later we would divide by 2, which is pretty simple to do as well. So by rationalizing those denominators, it made these hand calculations way simpler. Between you and I, to be totally honest, now that we have modern calculators that'll calculate this out to however many decimal places without having to use a table, the whole concept of rationalizing the denominator is really not as important as it was 40 or 50 years ago. Kind of an outdated act. But we still do it for a few reasons. One is for the practice. Math teachers are sadistic by nature, so I have to make you do it. But there's also some of our calculations, the only way to do the calculation is to rationalize the denominator. So if we look at rationalizing something like, well, like what we just did, but let's do it like this. 8 over 3 times the square root of 7. I do not have to multiply the denominator by the whole thing. That's 3 times the square root of 7. The only part I need to change is the square root of 7. So if I multiply by the square root of 7 on top and bottom, 8 times the square root of 7 is 8 times the square root of 7. 3 times the square root of 7 times the square root of 7. Well, the 3, think of this as 1 square root of 7. That's 3 times 1 is 3. Square root of 7 times the square root of 7 is 7. 3 times 7 is just 21. So that becomes 8 times the square root of 7 over 21. Here, I'm going to do one a little bit simpler here first. 9 times the square root of 3 over 5 times the square root of 2. When I go to rationalize this, it doesn't matter that there's already a root in the numerator. All I care about is the root in the denominator. I'm going to multiply by the square root of 2. On top, again, I always think of that as 1 square root of 2, 1 times the square root of 2. 9 times 1 is 9. Square root of 3 times the square root of 2 is square root of 6. Remember, I can multiply the objects of the radicals if they're the same index. So 3 times 2 makes 6, square root of 6. On bottom, 5 times 1 is 5. Square root of 2 times the square root of 2 is 2. So 5 times 2 is 10. So that's 9 square roots of 6 over 10. This one here looks pretty tough, and it can be. But sometimes before we go to rationalize that denominator, we want to check to see if we can reduce it all. $18 can be written as 9 times 2. I can take the square root of 9, if I separate it from the 2, square root of 9 is 3. 5 times 3 is 15. So the top of that becomes 15 square roots of 2. The bottom here does not work out to be quite so convenient, but I can break 10 into 2 times 5. Why do I bother with that? Because if I break that square root of 2 times 5 into the square root of 2 times the square root of 5, the square roots of 2 cancel out. And I now have 15 on top over 3 times the square root of 5. So far, all I have done there is reduce that fraction. I have not yet started to rationalize the denominator. Now that I've reduced it, however, we can rationalize it. I have the square root of 5 in the denominator. I'm going to multiply by the square root of 5. 15 times the square root of 5 is 15 times the square root of 5. 3 root 5 times root 5. You can think of this, 3 times 1 is 3. Square root of 5 times the square root of 5 is 5. 3 times 5 is 15. This one has an added bonus of I can reduce once I've done that. 15 divided by 15 is 1. That reduces to just the square root of 5. Let's test this. 5 times the square root of 18 divided by 3 times the square root of 10. Oops. .236. If I just do the square root of 5, I get 2.236. So it does work out to be the same. Some of you might have been looking at this reducing I did up here thinking, wow, that's kind of tricky. I don't know if I would have seen that. If you hadn't seen that, would it still work out? And the answer is, yeah, it probably should. If you had just started out, instead of reducing everything, just multiplying by the square root of 10. On top here, you would have 5 times the square root of 180. On bottom, 3 times 1 is 3, 10 times root 10 is 10, so that's 30. You could reduce the 5 and the 30 right away, but we don't have to because there's more coming. 180, I'm going to break down into 16 times the square root of 5, or 16 times 5. Or I could break it down in 2 to the 4th power times 5 if you wanted to, if we factored it. Now remember, this is a square root, so that index, even though it's not written there, is really a 2. 2 to the 4th power square root, that's 2 squared. What's left inside there is just the 5. Did I do that right? No, I didn't. Let me back step a little bit. That's not 2 to the 4th power. It's 2 squared times 3 squared times 5. So the 2 squared comes out to make a 2. The 3 squared comes out to make a 3. I'm left with the square root of 5. 5 times 2 times 3 multiplies to make 30, which will divide out, giving me just the square root of 5. Any questions? As you can see, reducing these things can get a little tricky. We can rationalize. So far, all we've done to rationalize the denominator is we've had just a single term down here. There's the radical times a number. And as long as that's all we have, we can rationalize the denominator for other radicals, other than just square roots. We might have 7 over 5 times the 3rd root of 10. To make this easier to rationalize, let's write it in exponential form. The 3rd root of 10 is really 10 to the power of 1/3. I don't need to multiply by another 3rd root of 10. That wouldn't do any good. The reason these worked up here is this was 5 times the square root of 2. I can write that as 5 times 2 to the 1/2. When I multiplied by another 2 to the 1/2, we still had the 5, but 2 to the 1/2, remember when we multiply, we add powers. 1/2 plus 1/2 is 1. That became 2 to the 1, and it eliminated the radical. Power of 1 is a whole number. Well, down here, since this is 10 to the 1/3, if I want those powers to add up to 1, I can't multiply by another 10 to the 1/3. I have to multiply by 10 to the 2/3. So now on top, 10 to the 2/3 is the 3rd root of 10 squared. Remember, the numerator is the power, the denominator is the index of the root. Ten to the 1/3 times 10 to the 2/3 is 10. So 5 times 10 is 50. So this becomes 7 times the 3rd root of 10 squared is 100, all over 50. Let's look at another example of that. Let's do 11 over 3 times the 5th root of, oh, let's see here, 18. How am I going to rewrite this denominator? 3 times the 5th root of 18 is going to become 3 times what? (18 to the power of 1/5). To get rid of that radical, what do I need to multiply that by? (18 to the 4/5). Very good. On top, 11 times 18 to the 4/5. Well, that's going to be 11 times, what's the index of my root going to be here? 5, good. And 18 to the power of 4. On bottom here, 18 to the 1/5 times 18 to the 4/5 is just 18. 3 times 18 is 54. We are not done here. Well, we could take 18 to the 4th power, but 18, remember, factors to 2 squared times 3. Let's take that to the 4th power. 2 squared to the 4th power is 2 to the 8th. 3 to the 4th power is 3 to the 4th. The reason I did that is now I see that I can pull out 5 of these 2's. There's 8 2's in the factors because it's 2 to the 8th. I can pull out 5 of them to make a 2.
Isn't it 2 times 3 to the 2nd power?
Ah, thank you. Good catch. Yes, it's not 2 squared to the times 3, it's 2 times 3 squared. So that's going to give us 2 to the 4th power times 3 to the 8th. So it's the 3 that we can actually pull out. And we're going to split that 3 to the 5th times 3 to the 3rd. The 3 to the 5th comes out, multiplying our 11 by 3. So that's 33. Times the 5th, what's left inside is 2 to the 4th and 3 to the 3rd over 54. There's still a lot of things happening here. Both 3 and 54 can divide by 3. 33 divided by 3 is 11. 54 divided by 3 is 18. On the inside here, 2 to the 4th is 16. 3 to the 3rd is 27. We do have to multiply out 16 times 27. 432. So this becomes 11 times the 5th root of 432 over 18. Yeah, I know, that's exhausting. If it's not just a single term, a single radical times a number in the denominator, here this is 2 terms. 8 minus 2 square roots of 5 is a 2-digit number. It's 2 terms. That's where we use that conjugate, and we use the conjugate of the denominator. The denominator here is 8 minus 2 root 5. Its conjugate is 8 plus 2 root 5. We have to multiply both the numerator and denominator. 7 times 8 is 56. 7 times 2 root 5 is 14 root 5. On bottom, This is going to take a little bit more time. 8 times 8 is 64. 8 times 2 root 5. Well, 8 times 2 is 16. Root 5. Negative 2 root 5 times 8. Negative 2 times 8 is negative 16. Root 5. Negative 2 root 5 times positive 2 root 5. Forgot. Negative 2 times positive 2 is negative 4. Root 5 times root 5 is 5. Negative 4 times 5 is a negative 20. So over here, positive 16 root 5 and negative 16 root 5 cancel out. 64 and negative 20 make 44. Are we done? What can we still do? Every term here is divisible by 2. Very good. 56 divided by 2 is 28. 14 divided by 2 is 7. So 14 root 5 divided by 2 is 7 root 5. 44 divided by 2 is 22. So that's 28 plus 7 times the square root of 5 divided by 22. Any questions? I'm going to have you guys try one. Actually, I'm going to have you guys try two. Rationalize the denominator of that one and this one. Oh, come on now. So 9 over 2 root 5 plus 7, and 7 over 5 times the fourth root of 3. I'll give you a couple minutes to do those. You might not quite be done yet, but let's take a look. So for the first one here, what are we going to multiply this by? Two root 5 minus 7 is the conjugate. It's the same terms, but we change it from a plus to a minus. So now on top, 9 times 2 root 5 is 18 root 5. 9 times negative 7 is a negative 63. That's our new numerator. On bottom, 2 root 5 times 2 root 5 is 20. 2 root 5 times negative 7 is negative 14 root 5. Positive 7 times 2 root 5 is positive 14 root 5. And 7 times 7 is a negative 49. So the negative 14 root 5 and positive 15, oops, that's a 14 there. Negative 14 root 5 and positive 14 root 5 should cancel out. 20 and negative 49 make negative 29. So this becomes over negative 29. We do not like having single numbers that are negative like that. So what they would most likely do is this. They would multiply both the numerator and denominator by a negative 1 to make this negative 18 root 5 plus 63 over 29. They might even go so far as to make this 63 minus 18 root 5 over 29. Any one of these three answers is acceptable to me, by the way. Just be aware that my math lab may ask you to rearrange that a bit. The second one over here, what do we have to multiply by the numerator and the denominator by? Where did I get that power of 3/4? There you go. The fourth root of 3 is really 3 to the power of 1/4, so doing times 3/4, the power of 3/4, it brings it up to 1. So 7 times 3 to the power of 3/4 is 7 times the fourth root of 3 to the third. Five times the fourth root of 3 times 3 to the third 3/4. 3 times, well, it becomes 3 to the 1, which is just 3. 5 times 3 is 15. This still needs to be simplified a little bit. 3 to the third power is 27, so that's 7 times the fourth root of 27 over 15. Bless you. Occasionally we want to rationalize the numerator. The only time we really want to do that is if we have something like this, where we're dividing, and we know that when we divide by this, we're going to be taking its reciprocal. So since we know we're going to use its reciprocal, we occasionally want to rationalize the numerator. Well, it's going to be the exact same process. We would multiply by the square root of 5 on both top and bottom. That's going to give you 2 times, square root of 5 times square root of 5 is 5. So 2 times 5 is 10 over 9 root 5. This one we know is not going to flip over, so we'd still want to rationalize the denominator of that one. So we'd multiply by the square root of 3. That's giving me 7 times the square root of 3 over 3. Then you would go ahead and do your reciprocal and multiply. 7 root 3 over 3 times 9 root 5 over 10. We could cross cancel, by the way. The 9 and the 3 both divide by 3, giving us 1 and 3. 7 times 3 is 21. Root 3 times root 5 is root 15 over 1 times 10 is 10. Now that we've done all this, we can move on to the next step. We did things last week like this. Where we multiplied those rational expressions with those radical expressions, I should say. If we want to divide radical expressions, the way we do that is we put it in fraction form. Three plus 5 square roots of 2 over 7 plus 6 square roots of 3. Now all we have to do is rationalize our denominator. Of course, the conjugate is going to be 7 minus 6 root 3. Up here, of course, 7 minus 6 root 3. Now, this is by no means a short problem even yet. We still have to do this multiplication up here. I'm going to write that off to the side here. So we've got 3 times 7 is 21. 3 times negative 6 root 3 is negative 18 root 3. 5 root 2 times 7 is 35 root 2. 5 root 2 times negative 6 root 3 is a negative 30 root 6. That whole mess right there is my numerator. Not pretty at all. My denominator will be a lot neater. 7 times 7 is 49. 7 times negative 6 root 3 is negative 42 root 3. 6 root 3 times 7 is a positive 42 root 3. 6 root 3 times negative 6 root 3 is negative 108. Just double checking. It's been one of those days. So the negative 42 and positive 42 root 3 cancel out. 49 minus 108 is a negative 59. There we go. So negative 59. So what this means is our result is 21 minus 18 root 3 plus 35 root 2 minus 30 root 6 over negative 59. Now again, my math lab's probably going to ask you to do some things, like maybe eliminate that negative, so you'd multiply the top and bottom by negative 1. It might also ask you to put the radicals in a certain order with the highest object first. So the negative 21 would still be first. This is going to become positive 30 root 6 because we multiplied by the negative 1. Then it'd be a positive 18 root 3, then a negative 35 root 2. Going from largest index of the root to the smallest over 59. I would accept the answer either way. Either the way it is in the brown up here or rearranged like this. It doesn't matter to me. Some of the math grammar makes sense, some of it really doesn't. It's time for you guys to try one. Divide that one out. 2 minus 5 square roots of 2 divided by 7 plus 3 square roots of 2. What are we going to multiply both the numerator and denominator by?
minus 2.
7 minus 3 root 2. Very good. On top, we'll multiply this out. 2 times 7 is 14. 2 times negative 3 root 2 is negative 6 root 2. Negative 5 root 2 times 7 is a negative 35 root 2. Negative 5 root 2 times negative 3 root 2 is a positive 30. Giving us a numerator of 44 minus 41 root 2. On bottom, 7 times 7 is 49. 7 times negative 3 root 2 is negative 21 root 2. Positive 3 root 2 times 7 is positive 21 root 2. And 3 root 2 times negative 3 root 2 is a negative 18. So the negative 21 root 2 and positive 21 root 2 cancel out. 49 and negative 18 makes 31. 31 is not factorable. So we got 44 minus 41 root 2 over 31. Any questions? Well, let's look at equations with these radicals in them. The square root of 3x minus 2 equals 5. We would solve this just like we do any of our other equations. We have to undo what's been done. To figure out what's been done, we follow strict order of operations here. If I look at this, this is enclosing symbol, which means we have to do everything inside that radical first. So the first thing that was done was x was multiplied by 3. Then the 2 was subtracted from it. And then we did the square root. So to take that apart, to reverse that, we're going to get rid of the square root first. How do we reverse a square root? We square it. Good. So the square root squared cancels out, and that gives us just 3x minus 2. What was inside the square root is left over. 5 squared is 25. And now we just go from there. To solve that, we would start by add 2. 3x equals 27, and then divide by 3. X equals 9. This works with other radicals as well. Square root, or the third root, sorry, of 2x minus 7 equals 5. The opposite of third root is a power of 3. So the third root and the power of 3 cancel out, leaving us with just 2x minus 7 on the left side. 5 to the power of 3 is 125. And now we solve. We add 7. I'm going to assume you guys can solve from here. So we add 7. 2x equals 132. And we divide by 2. X equals 66. Not all of our radicals are set up quite so conveniently, so simply like that. Often we have things like this. Oh, let's see, what do I want to put in here? we might have something like this. So just like when we were solving linear equations, where there was sometimes things we had to do before we started to solve, same here. Before we start to solve a radical equation, we have to first isolate the radical, the root, in other words. So we got to basically solve this equation once before we even start to solve it. So to isolate the radical, it's been multiplied by 5 and 8 has been added. So we're going to reverse that. We're going to subtract 8. So we have 5 times the square root of 2x minus 1 equals 31. Oop, not 31. How about 15? And then we divide by 5 to get rid of the 5. All that's left over here is the square root of 2x minus 1. 15 divided by 5 is 3. Now that we've isolated the radical, now we can get rid of it. We're going to square both sides. Again, the root and the squared cancel out. We have 2x minus 1. 3 squared is 9. And now we go through the process again to solve the remaining equation. We add 1. 2x equals 10. And we divide by 2. X equals 5. Any questions there? We can make life a lot more complicated when we have equations with more than one radical in it. Here we have the square root of 2 minus 4 and also the square root of 3x plus 4. What we're going to do, there's multiple ways we could handle this. We could just square both sides the way they are, but it's usually simpler if we get one radical on each side. So I'm going to put this radical, I'll move since it's negative anyway, I'm going to add it to both sides to put it on the other side. So now what we have here is we have the square root of 2x minus 4 on this side equals 2 plus the square root of 3x plus 4 on this side. Now we're going to go ahead and square it. Well, on the left side, again, the radical and the squared cancel out. This is just 2x minus 4. On the right side, this is 2 plus the square root of 3x plus 4 times 2 plus the square root of 3x plus 4. Well, 2 times 2 is 4. 2 times the square root of 3x plus 4 is 2 square root of 3x plus 4. Square root of 3x plus 4 times 2 is another 2 square root of 3x plus 4. And the square root of 3x plus 4 times the square root of 3x plus 4 is just no square root, just 3x plus 4. So if we combine all that, we got 4 and 4 makes 8, plus 3x, 2 times the root, and another 2 times the root makes 4, times the square root of 3x plus 4. Now we only have one square root left in our problem, so we have to isolate that. So I'm going to subtract 8 from both sides and subtract 3x from both sides. What I have right now, 2 minus 3 is a negative 1x, or negative x. Negative 4 minus 8 is a negative 12. That equals 4 times the square root of 3x plus 4. Now, technically, we should divide by that 4 before we do anything else. So I've got negative 1/4 x minus 3 equals the square root of 3x plus 4. Now that that radical again is isolated, we'll get rid of it by squaring again. Negative 1/4 x minus 3 squared is negative 1/4 x minus 3 times negative 1/4 x minus 3. Negative 1/4 x times negative 1/4 x is a positive 1/16 x squared. Negative 1/4 x times negative 3 is a positive 3/4 x. Negative 3 times negative 3/4 x is another positive 3/4 x. And negative 3 times negative 3 is a positive 9. So we've got 1/16 x squared. 3/4 plus 3/4 is 1.5 x plus 9 equals, on the right side, the root and the squared cancel out. That's 3x plus 4. So now, this is a radical. There's an x squared in it. And when we have an equation that has an x squared and an x, we solve it by factoring. So we subtract 3x, and we subtract 4 to set that to 0. So this is 1/16 x squared minus 1.5 x plus 5 equals 0. And then we would go about factoring that. This is a pretty ugly factoring. But we know that 1/16 x squared can be 1/4 x times 1/4 x. 5 can either be 5 times 1 or negative 5 times negative 1. That actually checks out. If we do the outside product and the inside product, we will get negative 1/2 x. We'll have negative 5/4 plus negative 1/4 is negative 6/4. So 1/4 x minus 5 equals 0, or 1/4 x minus 1 equals 0. And we solve each of them. I'm going to trust that you can solve them. This one gives us x equals 20. This one gives us x equals 4. So either x equals 20 or x equals 4. And I am at our time here. So the homework assignment that covers what we did today is homework 13A. Remember that due today is the homework 12 A, B, and C, and quiz 12. We will go over solving more of these radical expressions, radical equations tomorrow, and then we'll pick up from there. You guys have a good day. We'll see you tomorrow.